April 14th, 1900, Machinery Hall, Paris World Exposition. American machine tool manufacturers watched in silence as French engineers from Schneider demonstrated their latest cutting lathe. The tool bit into a steel forging, removing material at speeds that should have been impossible. More remarkable still, the cutting edge glowed cherry red from friction heat, yet continued to slice through hardened steel like a knife through warm butter. The American delegation shifted uncomfortably. Their own tools, displayed in a smaller pavilion across the hall, operated at conventional speeds, stopping every few minutes so cutting edges could cool. Without cooling, carbon steel tools lost their temper, their hardness, becoming useless soft metal. This was known. This was physics. Yet here were the French, apparently defying fundamental metallurgical principles. The humiliation was complete when a Schneider engineer announced cutting speeds of 90 feet per minute, triple what American tools achieved. Reporters from Le Figaro and The Times scribbled notes. German observers from Krupp nodded approvingly, recognizing technology that matched their own recent developments. American manufacturing supremacy, built over decades of Yankee ingenuity and industrial expansion, died that afternoon on the Champ de Mars. Or so it seemed. But 3,000 miles away in Bethlehem, Pennsylvania, two men had already solved the problem the French were now demonstrating. They'd solved it 18 months earlier, in fact, through a brutally systematic experimental campaign that consumed 26,000 pounds of steel and nearly broke Bethlehem Steel's research budget. Frederick Winslow Taylor and Monsell White had created tools that could cut while glowing red hot, at speeds that made the French demonstration look conservative. They just hadn't told anyone yet. The patent wasn't finalized. The process remained secret. And Taylor, watching from the American section of Machinery Hall, carried in his pocket a cutting tool that would, within days, shock the industrial world and establish American dominance in manufacturing for the next half-century. First, though, he had to let the French finish their show. The problem facing American manufacturing in 1898 was brutally simple. Carbon steel cutting tools could operate at 25 to 30 feet per minute before heat destroyed their cutting edge. Push them faster and the steel softened. The carefully hardened surface lost its temper, and the tool became worthless. Machine shops across America spent 80% of their productive time with tools sitting idle, waiting to cool. Building a single naval gun barrel required 6 weeks of machining time. The British did it in 4, the Germans in 3. Frederick Winslow Taylor had spent 20 years obsessing over this limitation. Born in 1856 to a wealthy Philadelphia Quaker family, he'd deliberately chosen the factory floor over Harvard, apprenticing as a pattern maker before rising to chief engineer at Midvale Steel. Taylor was not a metallurgist. He was a mechanical engineer with a stopwatch fixation and an unshakable belief that every industrial process could be optimized through systematic measurement. His time and motion studies had revolutionized factory management. His scientific approach to workflows had doubled productivity in shops across Pennsylvania. But none of it mattered if the tools themselves couldn't cut faster. In 1898, Bethlehem Steel gave Taylor unlimited access to their experimental shop, partnering him with Monsell White, the company's chief metallurgist. White understood chemistry. Taylor understood cutting. Together, they began the most comprehensive tool steel research program ever attempted. The variables were staggering: steel composition, carbon content, tungsten percentage, chromium additions, manganese levels, heating temperature, heating duration, cooling method, quenching medium, air cooling versus oil, water versus lead baths, slow heating versus rapid. Each combination required test cuts, measurements, duration trials. Over 26 months, they conducted between 30,000 and 50,000 individual cutting tests. The experimental shop generated mountains of steel shavings, 26,000 pounds of curled metal waste piling up outside the building. Bethlehem's accountants watched in horror as research costs spiraled into what would be millions in modern currency. But Taylor kept meticulous records of every test, every failure, every marginal improvement. The breakthrough came not as a single eureka moment, but through pattern recognition across thousands of failed attempts. Tools heated to conventional temperatures, around 1,500 degrees Fahrenheit, performed as expected, adequate but unremarkable. But tools heated far beyond the point where metallurgical theory said they should lose all hardness, past 2,000 degrees until they glowed white-hot, then cooled and reheated to a precise secondary temperature. These tools did something impossible. They cut steel while glowing red. They maintained their hardness at temperatures that should have destroyed it. They removed metal 3 times faster than any carbon steel tool ever made. The chemistry behind this miracle remained mysterious. Taylor and White discovered it through brute empiricism, testing every combination until the data revealed truth. What they'd stumbled upon was carbide formation, the transformation of steel's internal structure at extreme temperatures, tungsten at 18% concentration, chromium at 4%, carbon at 0.67%, heated to between 2,150 and 2,400 degrees Fahrenheit, air-cooled, then reheated to 1,800 degrees and quenched. This produced a cutting tool that defied everything metallurgists thought they knew. The first successful demonstration happened in Bethlehem's experimental shop in late 1899. A lathe operator engaged a Taylor-White tool against a steel forging, advancing the cutting speed to 40 feet per minute, then 50, then 60. The tool heated from friction, glowing dull red. It kept cutting. At 90 feet per minute, triple conventional speeds, the tip blazed cherry red in the dim shop light. Yet the steel shavings continued flowing smooth and clean. The surface finish remained precise, and the tool showed no signs of failure. Bethlehem's management didn't believe it. They demanded repeated tests with different operators, different machines, different steel batches. Every test produced identical results. The impossible had become reproducible. Taylor faced a decision. The patent application sat incomplete. The exact process remained secret. Competitors would pay fortunes for this knowledge, but the Paris Exposition offered a stage, a chance to demonstrate American technological superiority before the world's engineers, before the French, who thought they led in cutting tools, before the Germans who dominated steel metallurgy, before the British whose Sheffield factories had manufactured the world's finest tools for a century. Taylor shipped a specially prepared lathe to Paris, along with a selection of Taylor-White tools that appeared indistinguishable from ordinary cutting bits. The demonstration was scheduled for April 1900 in Machinery Hall, where 50 million visitors would pass through over 6 months of exposition. French Schneider works had already impressed crowds with their advanced cutting tools. German Krupp displayed precision machinery that reflected decades of engineering excellence. British manufacturers showcased Sheffield steel, legendary for quality. The American pavilion, smaller and less ornate, attracted skeptical European engineers who doubted Yankee claims of innovation. The demonstration began unremarkably. A large steel forging mounted in the lathe, cutting speed set to 40 feet per minute. Observers nodded. Adequate performance. Nothing special. Taylor increased in speed to 50 feet per minute. The tool heated as expected. Carbon steel would begin failing at this point, requiring cool down. The Taylor-White tool continued cutting clean. At 60 feet per minute, engineers pressed closer. Something was different. The tool glowed dull red from friction heat, yet the cutting action remained smooth, shavings flowing in perfect spirals. At 90 feet per minute, physics appeared to surrender. The cutting edge blazed cherry red, visible even in daylight streaming through Machinery Hall's glass roof. The tool removed a 1/4-inch depth of cut across a 12-inch facing width, maintaining tolerances that precision work demanded. For 28 continuous minutes, The tool cut without pause, without cooling, without the slightest indication of failure. Normal carbon steel tools required replacement every 3 to 4 minutes under far gentler conditions. A French engineer demanded to examine the tool, to touch the forging, to verify this wasn't theatrical deception using soft iron instead of hardened steel. Everything proved legitimate. The stunned silence broke into pandemonium. Lee Figaro reported that Americans had revolutionized metal cutting. German engineers from Krupp offered to purchase tools immediately. Taylor refused. British observers from Sheffield admitted their obsolescence with the quiet dignity of craftsmen recognizing superior work. The Taylor-White process won the Exposition's gold medal for machine tools, the highest award given. Bethlehem Steel implemented high-speed steel across its machine shops within months of the Paris triumph. Naval gun barrel production time collapsed from 6 weeks to 10 days. Despite tools costing 6 times more than carbon steel, $3 versus 50 cents, the productivity gains made them economically inevitable. Machining time dropped 50 to 70% for major components. American factories could suddenly produce what previously required triple the labor and time. The automobile industry's explosion depended entirely on this innovation. When Henry Ford introduced the Model T in 1908, his production plans required machining operations at speeds impossible with carbon steel tools. By 1913, Ford's Highland Park plant consumed 15,000 high-speed steel tools daily, cutting and drilling and milling the components that rolled off America's first moving assembly line. Without Taylor-White steel, the automotive revolution stalls remains a European luxury craft rather than American mass production. Arms manufacturers retooled immediately. Springfield Armory, Colt, and Remington adopted high-speed steel for rifle production. Barrel rifling time, the critical bottleneck in firearms manufacturing, dropped from 4 hours to 45 minutes. When the Great War erupted in August 1914, this capacity determined which nations could arm their soldiers. American factories, operating with high-speed steel tooling, shipped weapons to Britain and France while maintaining neutrality. French artillery plants, struggling with fuse production using outdated carbon steel tools, managed 2,000 units weekly. American plants with high-speed steel produced 10,000. Germany faced a critical disadvantage. Tungsten, essential for high-speed steel production, came from limited sources. American mines in Colorado and California supplied domestic needs. Germany depended on imports from neutral Sweden and Spain, supplies that Allied blockades threatened constantly. When America entered the war in April 1917, the industrial advantage became overwhelming. The nation needed to arm 4 million soldiers from a standing army of 200,000. Springfield rifle production ramped from 500 monthly to 5,000. High-speed steel tools made this possible. The Browning automatic rifle, with its intricate machining requirements, could only be mass-produced using Taylor-White tooling. Liberty aircraft engines contained over 6,000 machined parts each. Production targets that seemed fantasy became routine. In 18 months of war, American factories produced 15 million artillery shells. Germany managed 12 million across 4 years of total mobilization. The difference was high-speed steel multiplying worker productivity by factors of 3 or 4. One American machinist with Taylor-White tools equaled 3 European workers using carbon steel. When millions of men left for battlefields, this multiplication proved decisive. Frederick Taylor died in 1915. Just months before American entry into the war, his tools would help win. He never saw high-speed steel armed democracy soldiers, never witnessed the production miracles his obsessive experimentation enabled. Monsell White continued development work, but Taylor's name remained attached to the process, linked forever with scientific management and stopwatch studies that made him controversial. The tools themselves carried no controversy. They simply worked. World War II demanded even greater production miracles. The B-24 Liberator bomber contained 1.2 million machined parts. America built 18,500 of them. Each M1 Garand rifle required 8 hours of barrel production time with high-speed steel. Carbon steel would have needed 40. 50,000 Sherman tanks rolled from American factories, each requiring thousands of high-speed cutting operations. The arsenal of democracy ran on tools that cut while glowing red. By 1945, high-speed steel was universal, no longer an American advantage, but an industrial standard. Yet American production capacity, built on half a century of high-speed steel experience, remained unmatched. Today, the descendants of Taylor White tools cut metal in every machine shop from Ohio to Shanghai. Drill bits, saw blades, milling cutters, taps, reamers. A $2 billion global industry producing billions of tools annually, all using principles discovered through 26,000 pounds of steel shavings and 30,000 systematic experiments in a Bethlehem shop. In 1900, France demonstrated tools that could cut hot. America demonstrated tools that cut while hot, maintaining their edge at temperatures that should have destroyed them. The difference was everything. Taylor wanted machines to stop wasting time cooling down. Instead, he made American factories the most productive on Earth. The tool that ran red hot in Paris is still cutting.